here we go. So for this purpose, we're going to use a sine waveform dataset. So we're going to generate this out of with Python. It's really not that complicated. I can show you in a bit. Then what we're the number of observations in this dataset we're going to have are almost like almost 8,000 observations. This is going to be one feature only, and we're going to use the past data for the future, this future, the predictor of the future, as a predictor, and any other future window that we want to predict, we're going to use it as a target. The relationship we want to learn essentially is the temporal relationship of the sine wave, which is a cyclical sine wave pattern, as you might be familiar with from trigonometry. And the way we're going to split up the data set is going to be 70% to 10% for validation and 20% for test data. The data will actually follow naturally in the same fashion. So first we start with a train data set. We train the model on the train data set. While we're training the data set on the while we're training the model on the train data set, we're going to use the validation part of the data set to be testing it at all times, see how well it's learning. And once the model converges, we're going to deploy that model on the test data set. Right? And for the purpose of modeling the LSTM network, we are going to use a fairly simple LSTM model, which we're going to build with Keras. We're going to have two hidden layers of the LSTM network, one of 32 nodes and one of 16 nodes. We're going to use the ReLU activation function, which normally is applied in LSTM networks to learn any nonlinear relationship between predicted features and target. And yeah, loss function is mean absolute error, and we're gonna have 10 epochs. We're gonna run this for 10 epochs, and we're gonna use also a stop function for the model. So while the model is converging, we don't want to run all full 10 epochs. Essentially, we want to run only enough epochs so that we can get enough of a good training of the model. We use also patience of 2. So you'll see how this works in a little bit. And what we want to predict is going to be the next 64 steps ahead. So the 64 steps ahead will be essentially one full sinus wave cycle ahead. And the reason I decided to model this in that way with this sine wave function is just to show you how well the LSTM network learns the patterns over time. And then you can usually you can play with other data sets, like real data sets, to see how this performs on that. But if you build yourself a test like this of a sine wave prediction, you can get to find out lots of things about the way the LSTM networks work overall. Yeah, we're gonna use the following evaluation metrics, and let's just crack on. This is the code I want to show you now, and just to show you exactly how it runs, I'm gonna run it while I'm talking, just to be able to give you a little bit of to give myself a little bit of head start here, so you can see it freshly worked, and I'll explain out all the steps. So yeah, first of all, just like with any other code, we need to import all the required libraries for modeling this scenario. Then what we're doing is we're generating the data set, which is made by first generating the time sequence and then using this time sequence for generating the sine waveform. just for some clarification, we use this to generate the sine waveform. We use the NumPy function of sine wave, and that function takes in the radians, like a data type of it takes data in radians, which is the angle essentially of the sine waveform, and repeats a number of times. You can see the plot here. This is a cyclical pattern of the sine waveform, and the sine waveform was chosen because, like, essentially, when you're generating data like this is not a very much of a real world scenario. It's ideal scenario where your data is absolutely complete. You don't have any errors, and there's no noise as well. But you have something that is repetitive, highly repetitive, and you should be able to model this almost fully ideally with the LSTM network. LSTM networks, as you might know, are very popular for learning the long-term and the short-term temporal relationship between features. So this is any patterns in long-term, like seasonal patterns of weather data, or in short term, something like daily patterns. It's very easy to model with LSTM networks. So to produce this modeling scenario, we're using a function to generate the datasets here from. I provided a reference here from Machine Learning Mastery. Machine Learning Mastery is very popular online. He has produced a lot of material on time series modeling. I recommend you to go and check it out. And then what essentially what this formula does is it sets up some parameters, like what is the lag, the n steps ahead, the target index. This is the column which we use for as a target, and I'll explain a bit further how we have modeled this. But the inputs we have for this function are the following. We have a lag of 256 points. We're gonna model the prediction window for 64 points ahead. We have 70% we're gonna use for train data, for training the model. 10%, which is the difference between the train share and the validation share, which is 10%, we're going to use for validation of the model, and the rest we're going to use for test data, as we showed earlier in the slides. We have 10 epochs. As I mentioned, we have later set up an early stop function. We use batch size 1, learning rate of 0.001. And all these data inputs play in some way either in the pre-processing of the data set before we feed it to the neural network. So the lag is provided into the function we mentioned earlier. The lag is just how many portions, like in what portions of data we're going to provide into the training to produce the next 64 steps ahead. So I will show you now another step here to in the processing is to set up the shape of the data. So we need to reshape it into the following. You see the observations and the feature number here. So this shape is important when working with neural networks, particularly with LSTM networks here, which is a type of recurrent networks, and they all take the data in this sort of shape. Now here we apply the scaling of the data set. So when we're working with neural networks, we need to scale as well the data set. I've made another video of scaling and inverse scaling for this data set. You'll see it. Actually, it's a data set. It's not this data set, but I recommend you to go and check it out if you haven't. And then what we have is we use min-max scaler. We use the So we fit the data here, we transform it between, and the data transform in 0 to 1. And scale 0 to 1. It is always important to scale the data when you feed into neural networks because the neural networks converge faster. They don't produce errors, and also it removes any scale irregularities between features. And now we're going to, what we're doing in this field here is we're setting up we're feeding the scale data, and we are chopping it into the test part and the train part and the test part of the dataset. So X becomes the train observations, which we're going to use, and the Y is the test observations. Then what we're doing is we split up the dataset to the train X and Y part, the test dataset, which also has an X portion and Y portion, the predictor and the target portion. Similarly with the validation dataset, as we mentioned earlier, we have a number of ratios to chop this data into. And here you can see the shape of the training dataset, the way we're going to feed it into the LSTM network. We set up the LSTM network as follows. Here we're using the Keras library to do that, which is based on TensorFlow. And what we're doing here is we set up this two-layer model which has 32 nodes in the beginning, 16 nodes later. As you can see the activation function, that the shape of the models, as we mentioned, is required in particular type. Here we feed the shape of it. This is when we're modeling with LSTMs, it's very important that you set up return sequences as true on the first layer, and the last layer we have before output is set up as false. When you're modeling multiple steps ahead, it is also very important to use the dense layer with the input of the number of steps you want ahead. So this is 64 steps ahead. This is the full cycle of the sine wave we mentioned that we wanted to model ahead. You can see that the model is still converging here below. And then what we have is we have set up the early stopping function, which is set up using the validation loss, the patience of 2, and minimum steps ahead, minimum delta, essentially, for convergence. And this is the optimizer function, Adam, with learning rate and the loss function. Now, we also have here a small visualization of the way the model looks. What we have is the model still converges. You can see that the loss and the error rate are still reducing. They have dropped fairly well. What we're going to have later, actually, we're going to produce the output. We are going to turn this into a data frame, and then we're going to plot the results. And we're also going to see the evaluation metrics of the resulting waveform. And this looks like this is going to take a while. So let me come back when this is fully converged. We're back here. The model has converged. You can see that the validation loss and the validation error have reduced significantly. You can see the plot of both the training loss and the validation loss here. What we have produced as a result is the following. We have 1,472 data points, and for all these points we have produced 64 steps ahead of predictions. So this is 1472 multiplied by 64. This is the number of steps we have predicted ahead in total. But we're going to focus only on the first prediction we have made after, straight after we have actually we have trained the model. And what we're going to do here, yes, we're selecting exactly that. So we're predicting, we selected the first step of the test data set, and the first step. So this is the prediction we've made, the first step of the test data set, and we're plotting them. We're going to plot them also. So we select those and we turn them into data frames. You can see their, this is their shapes, and then this is the plot against each other. And you can see that the orange, the actual data, is following, is followed very well by our prediction. But there's still some little bit noise values here. You can see, especially when we are about to crest the wave. There's a few values which are a little bit outside, but you gotta understand that this is a very, very good prediction because here we're using synthetic data set which is generated now, so it doesn't have any errors in the data set itself before we put it into the neural networks. So it doesn't have any noise as well. So our model has learned very well the relationship of the sine wave and has managed to repeat it quite well. Then we here just looking at the evaluation metrics, we have very good correlation, which you might expect when you see such a good follow through of the prediction with actual data. A very good correlation means that our model has managed to learn very well the relationship of what we wanted to model to our predicted data in the future. And we have fairly low mean absolute error and root mean square error rates. The mean error is also very low. The minus sign shows that we are always a little bit below the actual data. Actually, our prediction is always just a little bit that lower with 2 here, 200s below 2000 is actually below the actual data. But the MAPE metric is always very difficult to put together to understand exactly what it means. The MAPE metric essentially doesn't have industry standard explanation of whether it is good or it is not. It's essentially just trying to measure in percentages the error. Here it doesn't seem to work very well, so we can completely disregard this. Please go try this small scenario I showed you on real data. But be aware of this sine wave training we've done and all the steps we've done there. I think this is a very good scenario to try first before you model real data, because it makes you understand how each parameter affects the learning of the neural networks. Some things that I haven't mentioned to you here are that we haven't actually inverted the data after we have scaled it, so that's very important for when you're working with real data. Here in this example, we didn't need to do that to show you that we had a good result of data at the end. But when you're working with real data, you will need to do inverse scaling. So for that, you can watch one of my other videos, which shows how to inverse scale the data set after you have made the prediction. And I'll show you later another example of how you can speed up the convergence by using GPU accelerated cuDNN STLM. It's a different type of LSTM layer, which will accelerate your convergence about 10 times faster. Thank you.